morning, everybody. Thank you very much for coming to this colloquium today, Severo Ochoa colloquium. That is a Vera Rubin colloquium. We have the honor and the pleasure to have here Professor Raffaella Morganti, who is a staff astronomer at the Netherlands Institute for Radio Astronomy, Astron, and professor at the Captain Institute in the University of Groningen, whichever in Dutch you say, it's Groningen or something like that. I don't know how to say it. Her career started with a thesis, a PhD thesis in Italy and the University of Bologna, and then she moved to, she had an ISO fellowship. She has worked at Astron, well, first in the Institute of Radio Astronomy in Bologna and the Australia Telescope National Facility, and then in Astron, where she was the head of the astronomy department during eight years. And since 2011, she's also affiliated with the Captain Institute in the University of Groningen, where she's full professor of structure and evolution of radio galaxies. In 2013, she received an advanced grant of €2.5 million from the European Research Council to explore the role of radio-loud active galactic nuclei in galaxy evolution. And the project combined the study of life cycle of radio AGN user LOFAR and with the study of their gas components. In 2014, I'm really proud to say so. I love it when I see that. She obtained the award of knighthood. This is in English. I will tell that later in Italian because I love it more, even if I don't say it correctly. Knighthood Commander of the Order of Star of Italy. So, Commendatore dell'Ordine della Stella d'Italia. And for you to know what it is, it's a decoration given to recognize, I read it as it is, recognize those expatriates and foreigners who made an outstanding contribution in the promotion of links and collaborations between Italy and other countries and or promotion of national prestige abroad. And this award is bestowed by decree of the President of the Italian Republic. So, she's author of more than 600 publications, more than 330 with referee, including Nature, Science, Nature Astronomy and Astrophysics Review, with more than 17,000 citations, with an extra 69. She's been invited to give invited talks in international meetings, only in the last 3 years and about 14 times. She has supervised or is supervised in 13 PhD theses and also having other relevant mentoring activity with supervision of master and summer students. She has participated and still participates in international committees, like, for instance, the European Research Council Advanced and Starting Grants, the Astronomy and Astrophysics Review Board of Editors. With respect to time allocation committees, he participates or has participated in ALMA, Effelsberg, HST, Westerbork, ING, ASCAP, and she is now panel chair and vice chair of the OPC at ESO. She has been SOC of amazing number of international meetings. Her scientific career is mainly focused on the study of AGNs, of active galactic nuclei, and in particular the properties of radio emission and the effect that it has on the surrounding interstellar medium, a field of research in which, obviously, you see she's an internationally recognized expert. She's also expert in radio interferometry, both continuum and line work, for instance, H1 and OCO, using, among others, radio telescope like LOFAR, Westerbork, VLA, and ALMA. She's part of the core team of LOFAR surveys and PI of the working group of nearby AGNs. She's deeply involved in other projects concerning the SKA Pathfinder precursors like Apertive, ASCAP, and MERCAT. For instance, she's a member of the Apertive survey team and participates in the definition of the Apertive surveys. And she's the principal investigator of the Apertive SHARP project, which stands for Search of H1 Absorption with Apertive. With respect to ASCAP, she's a member of the ASCAP FLASH executive team, with FLASH means First Large Absorption Survey. And she also participates in the ASCAP survey Wallaby. And with respect to MERCAT, she is part of the advisory board member of the MERCAT H1 Absorption Line Survey, and she also participates in LADUMA, looking at the distant universe with MERCAT. And she is also a member of the Square Kilometer Array Science Working Group on H1 surveys for galaxy evolution, being first author contribution to the SKA Science book. So we are really proud to have you here, Raffaella. Today she's speaking about neutral and molecular gas outflows as traces of impact of radio jets. So thank you very much.
Thank you for this introduction that expand my bio that I sent. Thank you for all this. And of course, thank you for the show. Just to illustrate how different radio jet can be, they can go from a very tiny structure that you can hardly see. This is an image at 6-second resolution, to huge, really important. And so there are these two scenarios that I'm sure you have heard before. The fact that jet can, AGN can produce outflow, and so a jet gas, and that's of course change the evolution of your host galaxy, or they can stop the cooling of the gas into the galaxy, and this also prevent some further evolution. And this is something that is part of many simulations, like this one is the illustrative simulation, where you see all this explosion repeating during the life of a galaxy. And so this is what usually is called the radio mode AGN, that I really don't like, because it's a bit misleading. Looks like that's the only case in which radio can do something. It's more on galaxies, on cluster scale, and should prevent the gas from cooling into the galaxy, and so be the fuel for new star formation. So what I'm going to show you instead is that even for outflow of this type, more connected to the usual quasar mode, you may make use of jets. And so on this scale, not only on cluster scale. And the other thing that I want to mention is that these simulations are wonderful, are nice to show, but still they have some problems. They have some problems about the way they would like, because clearly it's a complicated issue. There are different mechanisms that can play roles, from wind on parsec scale to radiation to jet, as I will show you. But the outflow are also multi-phase, so to quantify their impact is very difficult. In particular, there are the outflow of ionized gas are very common, but the outflow rate is modest. They don't really match what the simulation would like to see. And so it's interesting that in the last years, the component, the cold component, that for me is H1 and molecular gas, has become relevant because actually can maybe carry even more mass outflow rate. And then, of course, there is the role not only of the outflow, but the turbulence in general. So there are plenty of open questions. So my little contribution in all this is to see whether, at least for some part, there is a role for radio jet that tend to be a bit ignored. And I'll tell you why in a moment. So I would like to show you why it's worth considering this jet, and a few examples of work that we are doing. I'm not sure if they are nicely connected, but you will tell me. Using H1 and molecular gas. And the idea is to have some numbers, some input to give to people that do this cosmological simulation, if they want to listen to me, that I'm not actually fully sure. But OK, so why the jet? So one of the reasons why usually people say, well, why bother about the jet is because they are rare, they say. That is true. If you look at high-power jet, they are rare things. So this is a recent work from Sabater and Best. This is actually done with LOFAR, where there is the fraction of radio AGN as a function of the luminosity at your whatever favorite frequency you have. And this shows you that there is a very strong dependence on the mass of the host galaxy that people tend to forget about. So if you go to lower mass, indeed the fraction of radio AGN is not very high, even if you go to low luminosity. If you are on high mass galaxy, the fraction of radio AGN can go above 50%, especially if you go to low radioluminosity. So these are actually the radioluminosity that usually are called the radio quiet. So one of the messages of this talk is actually, don't be misled by the radio quiet. Just check what is the radio of your object. And so, of course, in this regime is more difficult to separate AGN and star forming, radio from AGN and star forming, as you can see here, how the two components evolve with the radioluminosity. But still, if you do separate, you find that there are plenty of radio AGN. Then the other thing that has happened in the last years is that people have found that even if you don't select a radio object, you select blind from Sloan, when you combine, when you stack radio object with the radioluminosity above a certain limit that is very low anyway, the width of your emission line may be larger. So like if you have even a little bit of radio, your oxygen tree line typically tend to be much larger. All to be confirmed maybe, but is an indication that even low luminosity AGN can give you some impact, can make some mess in your galaxy. And indeed there are a number of objects where this has been seen, low luminosity AGN, including from people in this building. So this group of low luminosity AGN and radio AGN that can affect your gas is definitely increasing with more detailed observation. But the thing that is more important for me is actually the progress that a numerical simulation has done. Typically, a jet is something very collimated that goes through your galaxy, and who cares about it? But actually, if you make a more realistic galaxy, if you make your jet surrounded by clumpy medium, then the effect of the jet can be different, can be larger. And this is illustrating this two simulation for two different power of the jet. But so if you have a powerful jet, it goes through relatively fast, but in the meantime is hitting all this cloud, and this is why the clumpy medium is important, and create a cocoon of shock gas that is over here. So the fact that there are this clump and this interaction of the jet with the clump created this shock cocoon that is much larger than the jet itself. So it's not the jet itself and the head of the jet that does the only damage, is the entire system. And this came up with a new numerical simulation. And if you have a lower luminosity jet, this poor jet struggles quite a lot to get out of this mess. That actually is no mess, it's just the ISM of your galaxy. And so it takes longer, and in the meantime it dumps all this energy in the medium and still create this kind of cocoon around, even if the luminosity is lower. And of course, these are the most common radio AGN, as I mentioned you before. So this kind of simulation sort of tell you that the jet can have a much broader impact, as a spatial impact, than the jet itself. And this is one of the things that we really would like to see. And we have some hint starting, but okay. And the various components of the gas can correspond to different phase of the gas that we observe, like the X-ray, the ionized gas, or the molecular NH1. So this is really, this new simulation make a prediction of what you are supposed to see if a jet interact with the medium. And note that these are these are young radio jets. So this simulation follow the phase in which a jet starts, is born, and start entering the medium. We are talking here about a few kiloparsec. So this is the first phase of the jet. And this is actually the one that seems to be the most interesting for the impact, and as I will show you in a moment. Okay, so good. So that was let's say, the introduction, and now I want to show you a few cases. And I thought to start with one that has a bit of everything in it. Is recent work, but not the last work we have done. And it's interesting because it's a Seyfert-2 galaxy, so it has a lot of radiation. It has more than enough radiation to ionize whatever and to push and to create outflow and all this. It's also a radio-quiet AGN, but not radio-silent. Always pay attention to this. So it's a radio-quiet, but still has a little jet. So let me show you what we have found with this. So this is my Seyfert galaxy, IC5063 in the south hemisphere, fortunately, because there are a good telescope also there. So this is in an early type kind of galaxy. John, you see the dust lane here. And this is the radio. This is the core, and there are 2 lobes. It's about a kiloparsec in size. So it's a tiny, typical Seyfert kind of radio emission. Small, a bit not super well behaved, but okay. So this object, we started studying because we observe in H1 as a huge disk of H1 along the dust lane, but in the center has this very broad H1 absorption component. It's more than 700 kilometers per second. So we did this in '98 when the feedback was not yet, so we didn't know what this was. But anyway, a very broad blue shifted absorption, so must be outflow, because this is absorption, so is in front of your lobe, and we could locate here. So this object was followed up in warm molecular gas, in ionized gas. It's really a mess. This is a slit along the radio axis, and you see the H alpha must be this one. So as a bit of everything. So what we did next was to study this object with ALMA, because it's nice to have the absorption, to see the outflow, but that's only where the radio is. So this is what we got from ALMA. It's a bit dark, but anyway, this is the disk of the galaxy. It's all, as you will see, regularly rotating. This is the inner part that is much brighter, and is the one coincident with actually the radio component that I showed you before. This is the same radio, but at higher frequency. This is still the core. That's okay. And then if you do a position velocity, if you take a position velocity along the radio axis, what you see is that at the location of the disk, everything goes very smooth, following the rotation curve that we expect for this object. But at the location of the radio, the molecular gas is really disturbed. In particular, at this location of the lobe, where we knew there was a strong outflow from the H1. So despite having a lot of radiation, this shows us that is the radio doing the job to push aside the gas and to kinematically disturb. Actually, it does more than that. It also changes how can I say, the temperature and the physical condition of the gas. This is now the line ratio 3:2 to 1:0 of CO. That shows that the disk is similar in ratio, as a low ratio, is similar to normal spiral, while at the location of the radio emission, the ratio changes, becomes much higher. And so we could estimate some of the parameters that we think are important also for feedback, like the kinetic temperature of the gas, the density of the gas that is high and clumpy. The mass outflow rate, that is not huge, it's just 10 solar masses per year, more or less, so a very small fraction of the total ISM. But also what we could do was to say, okay, if this is what we think is happening in this galaxy, this is if I would have the galaxy face on, this is a jet and this is the disturbed gas, can I reproduce my position velocity? And this is the model position velocity that we extract from a simulation done with the parameter of this object. So reproducing quite nicely. So it looks like, despite being a Seyfert-2, despite having all this property, here is the jet that does a weak jet that does the job. So it's possible. I have to say, for the feedback business, that actually only a small fraction of the gas leaves the galaxy. And this is a recurrent kind of result that we find. So the effect seems to be more on the disturbing the gas, increasing the turbulence of the gas with this spread, but the gas that leaves the galaxy is only a minority. You can also study how you can have a molecular gas flowing and being hit and still be there. And we concluded that there is really a short cooling time. And this is dense gas that has a short cooling time. And so actually at the location, these are results from a simulation, at the location of around the jet is where the gas can cool quickly and reform the molecular gas. So anyway, so this looks like, and this is why I show first, because this seems to be an object where we can prove that the jet can do the job. Whether it does in every object, that's another matter, but can happen. And while all the phase of the gas are involved. And so, so we went on and now trying to find how common this could be. This is more complicated because well, it's more complicated. It's more complicated to have time at the telescope. In itself, it's not more complicated, but, and so we are just trying to find out how often you have a jet-driven outflow, and how can you say this. So what I would like, we don't have a molecular gas result yet, although we have an ongoing project, so that's for the next colloquium that I will give in, I don't know, next visit. But we have a project with H1 absorption that I would like to show you the result. So H1 absorption we do, yeah, it's just H1 in front of your radio source. So it's very powerful. It's a very powerful and cheap way to detect gas in this object that are typically too far away for H1 emission, so that's much easier to do. And H1 absorption is common in the radio galaxy, known since ages. And usually what you find is the H1 associated with the circumnuclear disk. But then recently what we find were also a broad wing of the H1 absorption. Broad meaning more than 1,000 kilometers per second. And those are a signature of outflow. And so we were looking for this in a sample of about 250 objects selected by Sloan and First. And so the interesting result of this is, just very quickly, is that we detect H1 in almost 30% of the radio galaxy. This is already in itself interesting because, yeah, these are galaxy at redshift up to 0.2 that usually you don't trace in H1 emission. And in 15% of those detection, 5% of the entire sample, we find outflow, blue shifted component, some more convincing than others, but blue shifted component up to more than 1,000 kilometers per second. But the really interesting thing is that all the detection of outflow are associated with sources that we classify as young radio sources. So the one, like the one that I show you in the simulation, jet that just started. So not older than 10 to the 5, 10 to the 6 years. We estimate from the radio properties. So that's interesting because it means that there is a connection between the radio and the presence of this H1 outflow. And so from this, just to give you the main result, we find that there are H1 outflow in a group of objects with mass outflow rate up to 50 solar masses per year, not more than this we find. This, we can derive the kinetic power of this in this range. And this is a very small fraction of the Eddington luminosity. So again, compared to what the simulation, the cosmological simulation predict, these outflow are not the spectacular one that you really energetically you would need for the feedback. But still, they are there. In a few cases, also of low luminosity, AGN, because we know the optica, we could also locate where the outflowing absorption is. That's more complicated because it requires a high resolution radio observation, H1 radio observation. This gets into the VLBI, either VLA, like in this case, that we could say this is one of the lobe of this galaxy, and the broad absorption, that is this part here, is located at the location of one of the lobe. So this was the only one that could do with VLBI, with the VLA. Other we have done with the VLBI, I'll show in a moment. But so with the higher spatial resolution, we could also say where the outflow was happening. And this is even better if you want to really associate the outflow with the jet. So, so let me just show you a couple of cases that we have follow up with the VLBI. This is probably the best case we have. Is this radio source, and this is the profile, the integrated H1 absorption profile with this component blue shifted of 1,000 kilometers per second. And if you go with the VLBI and look where this component here is, you find that is at this location, so at the location of the end of the southern jet here, and around it in the lobe. And is made of clump that actually has a property, they resemble very much the one of the jet simulation that I've shown you before. So the jet has to enter a clumpy medium, and this kind of density are the one that the simulation also requires. So that was a nice independent kind of check for the expectation of the simulation. So I just have one other object to show you from our VLBI campaign that is really, it's okay, VLBI is great. Of course, it's great, what can I say? But it's quite time-consuming in terms of getting the, disentangling the gas rotating normally, just rotating regularly in the galaxy from the gas that is outflowing. So that's a complicated issue, but we have been doing also for other objects like this one. And so here you see some of the outflowing gas, and this is the position velocity along the radio axis. And in this case, you see that some clump are present, are blue shifted about 600, 700 kilometers per second, also here, deviating from the regularly rotating gas, and we can locate it with the VLBI, and we can see that some of them are already present at few tenths of parsec from the nucleus. So the outflow starts already very close to the nucleus. The H1 outflow means that the gas can cool down so quickly to be present at this distance. In cases like this, that is a relatively large radio source, it's a few hundred parsec. Most of the outflow that we detect here in the integrated spectrum is actually resolved out in the VLBI, so that's always a problem. But that's probably part of the evolution of the jet as entered the medium. The first part is where it push everything out and then start breaking out the clouds and becomes more diffuse gas, more difficult to trace with the VLBI. But again, we could derive density and compare with cosmological simulation. So the second, let's say, take-home message that I wanted to say is the radio plasma seems to couple, and the couple is the key point for feedback, couple well with the ISM, at least in the phase in which the jet is young or restarted, because we think some of the objects, including this one, is one of the giant radio galaxies, but with a restarted radio source in the center. And there seems to be a clumpy medium in the H1. That is exactly what the simulation predict. And as I say, associated with young radio sources, that is also what the simulation predicts. So there is a nice theme that is coming up from these observations. Okay, so that was the H1. So I have two objects to show you as in the final part of the talk, two very different objects. So one is Okay, so you have all this outflow, nice, of H1 molecular gas. We can derive their energetic. They look not quite up to the prediction of this cosmological simulation. This is something to understand. But clearly the jet seems to have some impact, so we decided to pick one of the objects that we thought had to be, and of course we were wrong, but okay, thought had to be a prototype case of feedback in action. No better candidate. So what I want to show you is something that we just published, is an obscure radio quasar. So it's an obscure quasar, meaning has a strong emission line, blue shifted emission line, has everything, has even an ultra-fast outflow UFO in X-ray. So it's a strong AGN, optical AGN. But it's also a young radio source. This is the radio jet, powerful radio jet this time, on the scale of a few hundred parsec. So we thought this is a jet, or an AGN in general, that is clearing the medium around. So that's exactly what you expect in the feedback process. Except if you look at the line, emission line, optical emission line, and you estimate the, I think there is a bit, okay, you estimated the mass outflow rate is a fraction of solar mass per year, and the kinetic power is also very, very low, as you see here, 10 to the minus 5 Eddington. So maybe everything is happening in the molecular gas. There is where we should see the feedback in action. So we did the ALMA observation that I want to show you. Is also part of a merger that we see in the optical as everything. Okay, so this is what we got from the ALMA observation. This is CO. We did both a 1:0 and 3:2. A very high spatial resolution to match the size of the jet. That was the idea at the beginning. So you find the CO as a part of the tail in the merger. That's okay. That's what merger can do. So the tail that you see in oxygen 3 and in light, you see also in CO, and you have quite a massive, quite a large mass of CO in there, molecular gas in there. Then in the center, in the very center, a disk is forming. So this gas that is flowing in is actually forming a little circumnuclear disk in the very central part. That is this part, is a position velocity plot, and this is the velocity associated with the rotation. And then in the very, very center, there is a fast outflow. That is this, again, this is a position velocity plot. This is the gas, outflowing gas at 1,000 kilometers per second or thereabout. But the outflow is very massive, is our record holder. If you want, is 600 solar masses per year. That is quite amazing. But it's all concentrated in, let's say, in the inner 200 parsec. So this is what we didn't expect. We thought the molecular gas should have been blown out from the entire system, not just in the tiny inner part. So from this, just because there are radio people here, let me just show you. We did something interesting with the ALMA. We did the super resolution because this object is quite strong, so you could obtain the same resolution as the VLBI observation. So you can go from the 300 gigahertz to the 2.3 gigahertz of the VLBI. You can do spectral index. It's really, yeah, was an interesting object to study. Actually has a very strange spectral index, so I can talk for hours about this, so I'll skip. But so the jet is doing something very special in this object, and clearly there are signs of strong interaction, but it's all limited in a very small area. So this is not what the standard picture of feedback would, AGN-driven feedback would tell you. And actually, this is not the only case. After this, another object appeared in the literature with a similar, very, very massive molecular outflow, but very limited to the inner region. And so this object has actually not helped us, or has helped us, but in telling that maybe the feedback is indeed not so straightforward as we think. It's not going to be that your AGN is blowing out the entire system. But what we found and what we learned from this is that, first of all, you can create accretion disk and you can have outflow at the same time. So they are coexisting in your system. That's also very interesting. From the line ratio, we could do again, see that the region in the center have a physical condition very different from the one that are more relaxed and falling down. So the line ratio is again very high, the 3 to 2 to 1 to 0 in the center, where there is the effect of the AGN, clearly, something there. So the physical condition, in addition to the kinematic, are affected. So what we think is going on here is just that, you have this outflow in the inner part, but then either the jet or the radiation break out and form more a bubble that extend in your medium, and that's what will make some effect. And maybe the effect is actually not in the outflow that is so limited to the center, but the effect again of this expanding bubble is more in the preventing the gas from cooling. So to keep the gas around hot via shock, via interaction, whatever. Also, the depletion time is relatively short, so meaning that this object, this outflow will not go on forever. So outflow, as also expected from other studies, are maybe on a temporary scale. So let me finish off. Do I have 5 minutes? Yeah. With one object, just to complicate the thing, because, okay, so we are getting a picture of the outflow, the one driven by jets, but actually also the study that attribute outflow to wind or radiation are getting similar result. That the mass outflow rate and the kinematic maybe is not up to the level that simulation wants. So maybe there is some more going on in this object. And I just wanted to mention, because it connects also to some of the work done here in this place, with a low luminosity AGN and a low power jet, and what we find for this. So this is an object that we have studied for a number of reasons at different time. So it's, from the radio point of view, it's very interesting, because there is a tiny source of about 1 kiloparsec that we think is a new radio source, newly formed radio source, embedded at the center of a much larger, 200 kiloparsec, very low surface brightness radio emission. So we think this kind of system are telling us about the recurrent radio emission. So this is the old one, and this is the new one. So you have exactly the phase that you need for the feedback. You have to have a multiple phase. Okay, so that's great. Even better, all here there is this huge disk of H1. H1 emission is a nearby object. Is huge, is 80 kiloparsecs, something like that, maybe more. So we know everything about the kinematic of this gas. We have a rotation curve, we have velocity dispersion, we have everything. Okay, good. So in the center, here in the center, because there is this smaller radio source, we can trace the H1 also with the absorption. And this is good because it can tell us the kinematic of the gas on this sub-kiloparsec scale. Because the absorption only depends on the strength of the continuum, how much absorption you can detect. If you have a strong source like this one, you can detect even tiny amount of H1. Okay, so we did this, just to cut the story short. The width and the kinematic detected in absorption doesn't agree with just poorly rotating gas, the gas that would be just in this large disk. So if we extrapolate all the parameters from the model of dynamical model, this profile should have been much narrower and also blue shifted. And if you are interested, we can talk about this later. Also, the molecular gas, we only have an integrated profile from Iran, but the profile that is one of these, one of the blue one, of CO is exactly the same as the one in H1. That is a bit strange because the CO could have been a rotating disk. So we think that this object shows in the very inner part an increased turbulence both it doesn't show an outflow, but shows that the H1 and the molecular gas have a broader profile than expected just from the kinematic of the large-scale disk. And we think this must be connected with the fact that you have this jet expanding in this disk. So in this case, we don't have an outflow, so okay, one can just throw away, no outflow, not interesting, but actually the kinematic still looks disturbed, and disturbed in a way that we think could be attributed to the jet as enough energetic to do this. The optical properties of this object are linear, and we have been discussing linear in the past 2 hours in the other room, so not enough to do the job of this. So looks like it's really this tiny jet that could increase this turbulence. So this is a scheme of what may happen, the jet expanding in the large disk, and these are the low surface brightness lobe. And this could be the geometry, so this is the disk and the jet, because also the geometry is important in the numerical simulation, if the jet exits the disk perpendicularly or with some angle, and so cross the disk. So this is what we think is going on. And actually, for this object, we found Khalifa data where they kind of identify 2 regions on their, based on their line ratio, but now I'm not sure anymore, in which both liner kind of properties, but with this inner part having liner property that cannot be described by post-AGB star, but really need to be attributed to shocks. So we think that could make the story complete. Our jet is in this inner part, and we think that can propagate this shock perpendicular to the jet and affect a larger area. How large is this area of the galaxy is totally unclear. And this is something where would be nice, especially with all this IFU work, whether one could quantify, because, okay, the jet may create a cocoon, and this cocoon expand laterally, but for how long? Is 1 kiloparsec, is 10 kiloparsec? Because that's, of course, has relevance for the impact. So there are more and more of this low power AGN, low power radio jet, but also low luminosity AGN, that are studied. They are becoming in fashion. That's very good. So there are some reference here. Incomplete, I should put the one of Sarah now here to add. But so they are a poor radiator, but they can be efficiently dumping energy in the medium. So something to consider, to keep in mind. Oh, there was a movie. Okay. Let me summarize this flow of information that I gave you. So I think we are seeing from different kind of study we have done that the impact of that jet can impact the medium, maybe not in every condition, but they can do the job, and can be in combination with radiation or alternative to the radiation. So that's something also based, but something to keep in mind. so the coupling between the radioplasma and the ISM can be quite good. So particularly interesting is where when you have cases where we can pin down the location of the outflow, and that's something that takes time, but data are piling up, so maybe soon we will have some more statistics. The mass outflow that we derive, either from H1 or from molecular gas, are on this range with our top candidate that is much higher, but on average they are this, and they still are relatively low compared to bolometric or Eddington luminosity. So, so that's something that, yeah, to understand. There seems to be a connection, as I say, with the young radio source. That's also very intriguing and interesting. The effect that this outflow seems to have is not to clear all the gas, but to increase more the kinematical disturbance, maybe the turbulence, create a overpressure bubble of shock gas, so disturb the medium, but the gas that is disturbed will rain back. So it's not that it leaves the galaxy and that's it. And so important to consider also the turbulence, the effect of turbulence, and maybe the preventing of cooling, not only the outflow effect. And there's a general conclusion that maybe can be also a topic for some discussion later. So I would like to stress again that whatever is called the radio quiet doesn't have to be completely radio silent. So have a look at the radio data if there are available. I know it's a pain sometimes. The radio astronomers are not very good in putting the data in an easy way, but okay, we can help. And so, so there is still some question about the energetic of this outflow, and I think this is a common problem, not only for the jet-driven outflow. So really is something that requires some more, maybe we have to change our idea of feedback and how it works. And clearly is a large parameter space that needs to be explored, and so goes a bit slow, but we are working on that. And so that's, that was my story. Thank you.
Thank you very much, Raffaella. Is there any question? Yes, Ivan?
Thank you very much for the super nice talk. My question is regarding, to have a complete comparison of the simulations that you have shown with with observations. Perhaps it could be needed to have observations of the dense gas around the AGN. So can you make a prospect for observing that gas, perhaps in...
Let me just, because I show, so it's not the comparison is not straightforward, definitely. This one that is here was really done. This is the result of the simulation by putting the parameter of this galaxy, this specific galaxy. And so we knew all the parameter of the disk. So they made the disk rotating, all this. And we knew from ALMA some of the parameter of the interstellar medium. So we could convince people doing the simulation to extract from their simulation some observable, like this position velocity that took a while to convince them that was useful to do. So, so at the moment, if you want to do such a detailed comparison, there are really very few objects where can be done. because this is, you need the high spatial resolution of ALMA, so you not only detect the CO, but really to sample compared to the radio jet. And so I would say at the moment there are very, very few objects done in this way.
Yeah, I was thinking perhaps a little bit more on actually imaging the cold gas that you have around. And I was perhaps thinking that high resolution with SKA2 could allow to at least map the small clumps in H1, for example.
In H1, yeah. So in cases like this, you could do, but why to wait so long? No. What I mean is low far, yeah. Like this one. Which one? The last. This one. The resolution here of ALMA is. This 0.05 you don't detect much, but you could detect already this state. So these are resolution already relatively interesting for the simulation. So the kind of cloud that they put in, that they don't know whether they are correct. So actually the main input from our side was the density that helped them to constrain. The size of the cloud, yeah. I think there is a lot that can be done already with ALMA, if you get the time.
Raffaella, thank you for such a nice, clear and illuminating talk. I really enjoyed it. In fact, I kept having questions and then you have answered most of them, but let me ask a couple of points. The last issue that you brought forward is the fact that the accretion disk jet, the accretion disk in particular, doesn't have to be aligned with the disk, large scale disk of the galaxy. So that would imply that the jet will have a much stronger effect on the impact on the surroundings of the galaxy. And that is important, very important, because you do see the fact that this mechanism is claimed to work in galaxy evolutions, because you do see that you need something like this, about stellar masses of about 10 to the 0.7 or so, 10 to the 10.7. You see that the star formation efficiency in fact decreases a lot, so you need this sort of mechanism. Now, the point is, how would you? This is most important for the larger mass galaxy. How do you connect the effect, assuming that you have all the right conditions, that you impact a lot of the galaxy and to stop the efficiency of decrease the efficiency of star formation? How do you connect the radio, assuming you have the geometry, the radio power of our cycle with the stellar mass, with the mass of the galaxy?
You want to go down in mass? Or?
The more massive galaxies, you need a larger effect.
Maybe. I don't know. What?
We see more or less when we do the galaxy evolution, stellar populations, and age and efficiencies of star formation.
What do you mean with more effect? Because you need enough energy to be dumped in the medium. So that's the point which we are. I don't think you need.
Is the effect of lowering the star formation efficiency is larger than for smaller galaxies?
This is why maybe this radio jet, even the small one, can help you, because the optical alone doesn't work all the time, even for the large one. Correct?
Yes.
So what I'm claiming is also that you should not say, okay, this has some radiation. I mean, I see the line, I see the ionized gas, so that has to be the cause of my outflow or heating of the gas or whatever. So the two mechanisms, first of all, can go together. And maybe they have to go together to make the impact that you require. Otherwise, we are a bit stuck. That's one. And then you want to go to lower. Am I getting the question correctly?
Below 10.7, the feedback from supernova seems to be more efficient than from AGN.
Okay, so I think also that is a question now. But okay, let's assume that is done. So I'm only concentrating on the larger. Okay, and so you are wondering whether
why the effect of feedback is larger, implying that decreases the efficiency of star formation for larger galaxies.
Larger for larger galaxy.
To the radio activity.
Not to the power, because there is no really relation between the power and the mass of the galaxy. It's more the fraction of a galaxy that will have some radio in it. It's the plot that I showed at the very beginning. So it's more than, let's say, more than 50%. If you look carefully enough, they have a radio thing. While as you go low in mass, they are the famous, infamous 10%. So it's important, but there will be more than 50% will have a radio, but maybe a weak radio. So we should get a bit away only from the monster, like Cygnus. Those are rare, okay. And the question is, are these low luminosity radio jet doing really something? Because even if they are frequent and they do nothing, then it doesn't help. So it's more that there are many in this massive galaxy.
That you brought forward in the conclusion is, ideally, what would you like to have to the type of observations, or how many target you need to observe and to detect the absorption or the effect of the perturbance in the interstellar medium, a large enough sample so that you can be sure that the effect is there and quantified statistically?
You ask me how many I want. Well, so this one that we did in H1, absorption, was actually a kind of pilot survey to prepare for aperitif. We did 3 hours per object, very short, with the old vestibule. Cha-cha-cha, very, very. And we thought, well, we go so shallow, we don't detect anything. That's not true, so we detect 30% and many with the outflow. So, but that was by accident in a way that we did. So the idea was, okay, this will be done by ASCAP, aperitif, for the entire sky, blind. That's the idea. So H1 could be okay, except there are all the RFI, but okay. Molecular gas is really tough to get the ALMA time for sample, but now we manage. Clive managed. So now we have the 2 Jansky samples that will be observed all in CO in a uniform way. So we will be able to say also the young one and the old one, whether there is any difference. It's not a huge sample, but at least it's a sample. So that's what we, and I hope there will be other popping up by other people.
I have a question myself. It's concerning the restarted activity. So far as I understand, when you have is that you have had a jet before and then you have a new one, right? Because you determined from the radio properties that you have older ages and then you have new ages. So with respect to the models you've shown, you've compared the model. So I mean, do the models take into account that restarted activity? Because I guess that it's not the same thing. Oh.
No. Now we are working now because we know the first jet. So the first jet enter a medium and then switch off after a few times 10 to the 7, 10 to the 8. These are the typical age of a radio source. Switch off for how long? Because if it's switch off for a long time, the kind of the medium resettle, close the channel, and then a new jet start, and then it's a new jet. It has to fight in the same way. If the off phase is not too long, then there is still a channel kind of open. The new jet will go much faster and quickly. So this is an extra parameter that needs to go in the simulation. And they start to make a simulation about this. So it's a nice time to compare simulation and data. But it's a tricky business. But in many restarted, we see again the effect of this, the presence of this outflow. There are some beautiful cases.
Okay.
How many times do you see an AGN low energetic jet coexisting with galactic winds?
Wind. You mean with outflow in ionized gas? Very often, yeah.
Between these two events without using a VPT?
Interesting point, because actually one of the persons that put together this simulation of the jet in the medium, forming this cocoon, he also put together simulation of wind, that in a way they form also a cocoon of shocked gas. So if you want the two, if the model are correct, blah, 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 and all this, maybe after all, there is not a huge difference in the impact. This is energy sent to some kind of collimation, doing something, and essentially shocking the gas, heating the gas. So maybe the two mechanisms at the end, they are not making a huge difference. So actually, in most of the cases where we say is due to the jet is because we have either indication are young jet, so it's more likely, but even that is kind of a guess, or we have the location. So around the radio lobe, we have really for an handful of objects. So, and this object here, actually I cannot tell you whether it's the jet or the wind, radiation wind that really does the job. I can tell you that the jet very likely is disturbed, has hit something, has had interaction, has a strange morphology and spectral index. And so there could be something that has destroyed or so. But I cannot tell you for sure that in this case it's the jet instead of the wind. So that's, but usually we find, if we find the outflow of the ionized gas, we also find in the molecular or the H1.
Is there any other question? I'd like to tell you that Raffaella is staying here, so in the afternoon at starting at 4 or so, we will be in the Sala de Juntas, just to continue with the discussion. So all of you are welcome to come this afternoon. If there is any other question, and if not, we acknowledge again Raffaella. Thank you very much for such a nice talk.